All right, welcome back, everybody. Hope you've been enjoying integration in higher dimensions. We've been doing a lot of double integrals and doing a lot of fun things with them. Naturally, the next thing we're going to talk about is triple integrals, and we're going to start with Cartesian coordinates, so regular old rectangular coordinates, x, y, and z, which everybody knows and loves. Here's my boy Rene Descartes in the background, founder of said coordinate system, I assume. Okay, so first of all, why do this? Double integrals are already hard enough. Why do triple integrals? Um, to remind you here, when we were dealing with double integrals, they were a good way to help you find the area of a plane figure. So if you have some kind of a strange region R, and we integrate over that space, we integrate the function 1, we're going to figure out what the area of that shape is. Um, and this is all well and good. Hopefully, our dA here means it's our differential of area. So we're taking a small rectangle or a small. If we switch to polar coordinates, it's a small little piece of a sector. So dA is just a small area, and we're adding these all up. Essentially, it's an integral. So if we wanted to find the volume of a solid, which is just the next natural thing, we usually call solids D for whatever reason. And so we're going to have a triple integral here. And to type this in LaTeX, if anybody's interested, so actually up here for a double integral, it's backslash I N T. You do two i's for a double integral, and you do three i's, backslash IINT to make a triple integral. Do not do backslash int, backslash int, because that'll give you too much spacing and it doesn't look very nice. Okay, you'll notice here that we use dV instead of dA because we're going to take just a little piece of volume. Essentially, we're adding up a bunch of, I guess, hyper rectangles here, hyper cubes or something like that weird. We'll worry more about kind of that meaning in a little while. For now, the integrand is just going to be 1, so that this will in fact give us the volume, which is nice. Okay, so here's an example of a triple integral. This one, again, don't try to envision what's happening here. Technically, I guess we're finding the hypervolume of a four-dimensional figure, but let's just calculate what this thing is. So just as always, we start from the inside and we work our way out. So you notice that the inner integral is a dz. So we're going to anti-differentiate with respect to z first, the integrand, and we're going to get something like e to the x times yz plus z squared. Hope you all agree with that. And we're going to evaluate that from z equals 0 to z equals x plus y. So again, notice your bounds on your integral. Those are the bounds on z. If you plug those values in and do some algebra, you can clean this up a little bit, and we get the integrand gets more complicated. It usually does, but we've gotten rid of one of the integrals, right, by calculating it. So now we integrate again. This time we're integrating with respect to y, and you're noticing that here hopefully that y is ranging from 0 to x. So when we anti-differentiate with respect to y, we get again a kind of nasty formula that we're then going to integrate from 0 to x. From y equals 0 to y equals x, I should say. So again, we're integrating with respect to y. All this should look identical to what we just did with double integrals. It's just we're adding a third step, essentially. So plugging all that in, I'm getting something like 19/6 e to the x times x cubed. Now it's just a regular old, single integral, which you all know and love. To figure this one out, you'd have to use some kind of integration by parts, probably multiple times, or just punch it into a calculator or Wolframin, or do something, and you'll get the answer 19 times the quantity e squared plus 3 all over 3, whatever significance that might have for this problem. Okay, so again, it should look just like what we do with double integrals. Now we're adding a third one. Okay, so you'll recall that our good old friend Guido Fubini told us that we can interchange the order. And if you're working over a rectangular region, you can just straight up switch things around, and it's very nice. If you're working over a more general region, it's a little more complicated to switch things up because you have to think about the bounds, how the bounds are changing, but you can still change things around. and that's always a nice thing to have. So here are some examples of how kind of a general integral is going to look. You'll notice that there's actually quite a bit going on here. So my first integral here I'm doing for both of these is dz. And so z, in general, is going to be a function of x and y. That's why I've got h of xy and k of xy. Z is going to be a function of x and y. So the bounds on the inner integral are going to be the other two variables. It's going to be the two variables that are, I guess, being anti-differentiated second and third. Once we take care of this integral, which is the first thing that we're calculating, right, then you'll notice that I've got, we'll switch colors here, dy, right, or dx. The order, whatever order makes your calculations easier for you. But you'll notice if you've got dy, then your function is going to be f of x and g of x. It's going to be a function of the other variable. And similarly, if you have dx second, then you're going to have functions of y as your bounds here. Now, of course, a function of y could still be a constant function. So all these could be constants, and that would be really easy. But if you did want to really generalize this, then you would be in this situation. The last thing you'll notice is that the very outer integral is always going to be from a to b. It's always just going to be constants. Again, that doesn't have to be the case, but that's generally what things are going to be looking like. Or otherwise you'd have a function of, yet another variable coming out of this, which, it's not outside the realm of possibilities, but it's not super fun. Here's, well, a lot more examples of, I guess these are like all 6 possible orderings. Is this all the possibilities? Yeah, it is. So 3 factorial, right? So these are all the different orderings of dx, dy, and dz. And I've got them all here for you if you want to check them out. But again, just look at the inner integral. The bounds on the function are functions of the outer 2 variables and so on. And the very outer integral is always going to be just have constant bounds. Okay. So just to summarize what I was just saying there, we're always going to have constants for the very outermost integrals. The middle integral, the wording here is a little confusing maybe, but the limits for the middle integral is only allowed to involve the variable used in the outermost integral. So we go back to this page, the middle, what do we have in the middle here? The middle integral here is functions of x, and that's the outermost integral, outermost variable. Here the inner integral is functions of z, and that's z is the outermost variable. So that should always be happening. Let's see, let's go back here. And then of course the limits for the inner integral can only involve the variables in the 2 outermost integrals, or in other words, not the inner integral variable. So confusing, but hopefully it makes sense. You just watch this over and over if you need to, until it clicks. But hopefully it'll be more intuitive the more you look at it. Okay, so let's do an example with a triple integral. Let's imagine that we have a building. It's 8 meters wide and 16 meters long. It has a flat roof, but it is not horizontal flat roof. It's not parallel to the XY plane or anything. The roof, it is flat, but it's got its highest corner. So at one of the corners, it's going to be 12 meters high, and at the 2 adjacent corners, it's only going to be 10 meters high. So I think that means that the other corner would have to be at 8 meters high, but that's something that maybe you should check. So hopefully you can envision this kind of a slanted roof on top of a rectangular box, essentially. So what is the volume of the building? So if you think about this for a little while, hopefully it's clear to you. So I would probably have like x range from 0 to 8 because there's a rectangle at the bottom, right? So x would range from 0 to 8, y would range from 0 to 16, or maybe vice versa. You can switch that around if you'd like. But z, your height, is changing more so, right? Z is defined by some kind of a plane. And so hopefully you all remember from Forever Ago how to write an equation of a plane, where essentially we're given 3 points here, right? We're given the point so we know that it's 12 meters high at the back, so think of that as like the point 0, 0, 12. And then you can figure out the other 2 points as like 6, 0, 10, and 0, 8, 10, I guess. And once you've got those 3 points, then you all know how to write the equation of a plane. Anyways, if you don't remember that, practice that. Go back and try and find the equation of the plane. and then I believe you'll be able to find the following bounds for your integral. So I've set this up as so dx is my outermost variable, and x is ranging from 0 to 8. Dy is my next outermost variable, that's ranging from 0 to 16. And then z, let's see what color have I not used. Let's do this one. I've used that one. No, I haven't. Okay, that's good. dz is again ranging from 0 to not a constant, right? If it was a flat roof, this would be a piece of cake. Just go up to the you go up to the top and you have a rectangular prism. There's some slant here though, and so the equation for the plane most likely is going to be something like, z equals negative x over 4 minus y over 8 plus 12, and that's what's giving us the upper bound here. But again, that's something to check. Make sure you remember how to write equations of planes. And so, because my bound is a little bit, more complicated, that's why we're getting a more interesting answer than just length times width times height. And you'll notice that my integrand here is 1, because I'm just trying to find the volume, right? When you're just trying to find the volume of something, just like before, when we were only trying to find the area of something, your integrand is 1. Okay, cool. By the way, that if you want to calculate it, I just wolframed it again. I got 1,280, and that's going to be cubic meters. Don't forget, you all won't forget. You know this. Cubic units for volume, of course. Okay, let's do another example. Let's find the volume of the region bounded by these two paraboloids. Remember paraboloids? All these quadric surfaces are finally coming back because we can now do cool stuff with them. Okay, so right off the bat, hopefully this is pretty straightforward. Y is given as a function of x and z, so that means that I want to integrate with respect to y first. dy is going to be on the inside. Here's my dy. And y is ranging from x squared plus z squared to 16 minus 3z squared minus, or 3x squared minus z squared. Now, if you were to graph this, I would use Grapher or something. You would be able to see that, the top function is actually on top here. Or if you just think about it for a little bit, you can probably figure that out. But if you ever make the mistake of interchanging them, it's totally fine. You just multiply by a negative in the end, and you'll be in business. So hopefully the setup seems clear. I'm then choosing to do dz, and then lastly I'll do dx. And so I've got question marks on my bounds because we need to find those. We need to find the bounds here. Okay, so one way to do this, again, you can always graph these things if you'd like. I don't know. I have such a hard time visualizing them, and it's so rare to find good graphing software that you can actually see what's happening. But Grapher is a pretty good choice if you have a Mac. So, anyways, I just do everything algebraically, and hopefully it'll all fall into place. So, what you're going to do here is you're going to set these two equations equal to each other. And then solve for, I chose z to be in the middle, so I'm going to solve for z. If you wanted to do dy, dx, dz, then you would solve this for x. But I'm solving this equation for z, which is hopefully a piece of cake for you all, and I'm getting z is equal to plus or minus the square root of 8 minus 2x squared. And so that is going to give us the bounds for my middle integral. We're going to go from negative root 8 minus 2x squared to positive root 8 minus 2x squared. Let's go back to this equation again. This is just setting the two equations equal to each other because we still have to find the very outermost bounds, right? Which should be constants, by the way. Again, you'll notice here that I guess the inner integral is a function. It's functions of x and z on the top and bottom. The middle integral, the bounds on it, are only functions of x. And so the very outer one should be constants. Let's see if we can find those constants. So if we go back to this equation that we were dealing with just a moment ago, and do some more fancy algebra, we can rewrite this as the following formula, which is clearly an ellipse, right? It's a nice, beautiful elliptical shape. And so I hope that if you just think about this for a minute or two, you'll see that x can range anywhere from -2 to +2. It can't be any bigger than -2. It can't be any smaller than -2 or any larger than +2, because then this whole thing would be bigger than 1, and that would be a problem. So we've got an ellipse which ranges where the x value is going from -2 to +2, and that's going to give us our outer bounds on the integral. So that's it. That's what we would then calculate. It's going to be terrible because it's got so many variables. You're going to have to do a ton of trig substitution probably, but this is where Wolfram comes in handy. or a TI-89, or I don't know if you're viewing this in the distant future, some whatever machine you have. Let technology figure this out for you. Oh, I guess I did it already for you. The answer is 32 pi root 2. You're welcome. I, of course, did not do that by hand. I typed that into Wolfram. Okay, perfect. Let's do one last example. So here I've already got the integral set up for you, which I guess is pretty nice. But what you'll notice is that this does not look super easy because I've got this dy here. So the first step will be easy. So I'm doing dz first, and that'll be easy because there's no z in my integrand. But then I've got this dy, and I'm going to have to somehow integrate sine of y squared, and I'm not feeling good about that. Yeah, I feel like I would probably need a computer or something for that. And again, I guess we could just punch this whole thing into a computer from the get-go. But let's see if we can do a little trickery here. And of course, that trickery is to use Fubini and switch things around a little bit. Let's switch it up. So I would really like the y to come last because I really don't want to have to deal with that sine of y squared until the bitter end. And maybe some good will come out of this. So you'll notice that y originally is ranging from x to root pi over 2. If you switch this around, if you change the order, what you'll notice is that x is going to range from 0 to y, which is very nice. So kind of just like we did before double integrals, draw this feasible region and then split it up the other way. And when you do things this way, you can do the middle two integrals really easily. So we get integral from 0 to pi, root pi over 2. The middle two integrals, because we're integrating with respect to z and then with respect to x, but there is no z and x in my integrand, so I'm just going to get 2y. I'm just going to get the product of this rectangle here. So I'm getting 2 from this guy, 3 minus 1 is 2. I'm getting y from this guy, y minus 0 is y. So I'm just going to be getting 2y times the sine of y squared dy, and that integral looks beautiful. I can figure that out using u substitution and be done in no time. And it turns out we get a very nice answer here. The answer is 1. Again, you could have just plugged in the original triple integral into Wolfram or something, but if you're doing an exam or something where you're not going to have Wolfram, and not everybody has a calculator that can do this kind of magic, there are other ways of doing this. So feel free to switch the integrals around and switch the order of integration around, and sometimes, usually, you'll get an easier way to figure it out. Okay, so this has been fun. Cartesian coordinates. I hope you've enjoyed this and have fun practicing it. We will chat about this soon.